Imagine standing on a vast cosmic stage where all of existence emerges from a singular event so dense, so hot, and so unfathomably intense that it challenges our conventional notions of reality. For billions of years, this event, commonly called the Big Bang, has been the cornerstone of modern cosmological thinking, painting a picture of how the universe began and subsequently evolved. Yet the term Big Bang can be misleading. It conjures images of a violent explosion echoing through a pre-existing void. In reality, it's more accurate to say that every point in space suddenly began expanding from an ultra-compressed state, with space itself stretching out in all directions. If you can picture an unimaginably tiny balloon inflating at breakneck speed, you get a rough idea of what cosmologists think happened during those formative moments. Initially, this concept was met with skepticism. In the early 20th century, many scientists believed the universe had always existed in roughly the same form, and that it was essentially timeless. Einstein's general theory of relativity opened the door to the idea that space and time could be dynamic, but it was astronomer Edwin Hubble who delivered the first critical piece of observational evidence. By studying distant galaxies, Hubble noticed that their light was shifted toward the red end of the spectruma phenomenon, known as the redshift. The farther away a galaxy was, the more pronounced this redshift became, indicating that these galaxies were receding from us at accelerating speeds. It wasn't just that galaxies were drifting through a static space. Rather, space itself seemed to be expanding. This was a shocking revelation at the time, one that spurred new debates about whether the universe might have once been far smaller, denser, and hotter than it is today. But observational breakthroughs didn't stop there. In the mid-1960s, Arno Penzias and Robert Wilson accidentally discovered a faint microwave hiss in their radio antenna. At first, they tried to attribute it to technical glitches or even pigeon droppings on the equipment. Yet no matter what they did, the persistent background signal refused to vanish. Eventually, they realized they were detecting the cosmic microwave background radiation, CMB, the very afterglow of the hot, dense state that marked the infancy of the universe. The CMB is like a snapshot of the cosmos at around 380,000 years old, when hot plasma finally cooled enough for photons to travel freely across space without constantly colliding with charged particles. Today, those photons have stretched with the ongoing expansion, dropping into the microwave part of the electromagnetic spectrum. The discovery of the CMB bolstered the idea that our universe had, indeed, emerged from an earlier phase of extreme conditions. From this convergence of theory and evidence, the modern Big Bang theory blossomed. Yet the story of how the universe went from an overwhelmingly dense and superhot state to the vast cosmic tapestry we observe is intricately detailed and filled with fascinating subplots. In the very first fractions of a second, the universe is thought to have undergone a period of inflation, an exponential expansion that flung regions of space apart at speeds faster than the speed of light. This doesn't violate relativity, because it wasn't objects moving through space faster than light. Rather, space itself was expanding, carrying its contents along for the ride. Inflation helps explain why the universe looks largely the same in every direction, why it's so uniform on large-scale sand, also why small variations in density existed that later coalesced into galaxies and galaxy clusters. But let's dive deeper into those scorching early stages. Initially, at energies so high that temperatures soared to trillions of degrees, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces may have behaved in ways that defy our everyday experience. Particles could pop in and out of existence, merging, splitting, and transforming under the influence of quantum processes happening at breakneck pace. In this primeval soup, there were no atoms, just a hot plasma of quarks, electrons, photons, and other exotic particles. As the universe rapidly expanded, it also cooled. Soon, quarks joined together to form protons and neutrons. A few minutes later, the growing universe had cooled enough for these protons and neutrons to fuse and produce the first light nuclei, mostly hydrogen and helium with trace amounts of lithium. This short window of nucleosynthesis was crucial. It determined the basic chemical composition from which all future stars and galaxies would be built. Fast forward to the time shortly after 380,000 years. By then, the universe had cooled to a few thousand degrees Kelvin, allowing electrons to combine with nuclei and form neutral atoms. Suddenly, space became transparent to radiation photons, no longer scattered off free electrons. That is the moment imprinted in the CMB. This was also the start of the so-called Dark Ages, a period when the universe contained mostly neutral atoms, with no stars or galaxies to light up the darkness. It might sound like a quiet interval, but gravity was at work behind the scenes, gently drawing together regions of slightly higher density, which would eventually ignite as the first stars. These stellar pioneers were massive and short-lived, shining brightly and exploding violently in supernova blasts that enrich the surrounding gas with heavier elements carbon, oxygen, nitrogen, iron essential for forming future planets and biological life. Thus began the grand chemical evolution of the cosmos. Despite the success of the Big Bang model, alternative ideas have occasionally captured scientific imagination. One early rival was the steady-state theory, which proposed that while the universe expands, new matter is continuously created to keep the overall density the same. This theory once had notable proponents, but it began to falter when evidence for the CMB could not be reconciled with the steady-state framework. Other concepts, however, still linger on the edges of mainstream science. There's the idea of a cyclic universe, suggesting that the cosmos might go through endless cycles of expansion and contraction in infinite loop, rather than a one-time event. And there's the notion of a multiverse, in which our Big Bang is merely one bubble of reality, among countless others popping in and out of existence, within a grander, higher dimensional structure. While direct evidence for such ideas remains elusive, they demonstrate how the Big Bang theory, far from closing the book, has sparked even more audacious questions about the nature of reality itself. One of the biggest modern mysteries relates to the so-called dark components of the universe. Observations of galactic rotation curves and gravitational effects on light from distant galaxies suggest there is significant mass that neither emits nor absorbs light. We call this unseen mass dark matter. Then we have dark energy, a mysterious phenomenon responsible for accelerating the rate of cosmic expansion. Observations of distant supernovae in the late 1990s revealed that the universe's expansion isn't just continuing, it's speeding up. This was a monumental shock. Dark energy now appears to account for about 68% of the total energy budget of the universe, with dark matter around 27%, leaving a meager 5% for all the normal baryonic matter, everything we can see and touch. Understanding how dark matter and dark energy fit into the grand narrative of the Big Bang is a key frontier in modern cosmology. But let's circle back for a moment to the most perplexing question of all. What, if anything, happened before the Big Bang? Did time even exist in a fashion we can understand? Our known laws of physics break down when we try to extrapolate into that earliest moment, commonly called the Planck era, when the universe was so dense and hot that quantum effects of gravity become important. Some theories suggest that our universe might have emerged from a collapsing state of a previous universe, or perhaps it was born out of quantum fluctuations in a vacuum-like setting. Others propose that time is emergent, meaning it might not have existed in the same way before the Big Bang. There's no definitive resolution here, and researchers keep pushing the boundaries, hoping that advances in quantum gravity or string theory might one day shed light on this ultimate riddle. Meanwhile, technology and observational capabilities continue to evolve, allowing us to probe ever deeper into cosmic history. The James Webb Space Telescope, for instance, is giving us unprecedented views of the earliest galaxies that formed a few 100 million years after the Big Bang close to the end of the Dark Ages. By studying their structure, stellar populations, and chemical makeup, astronomers can test predictions of how matter first clumped together to ignite star formation. Observations of the CMB, particularly through missions like COBE, WMAP, and Planck have, map tiny temperature variations across the sky in exquisite detail. These variations are the seeds from which galaxies grew. Any anomaly in those patterns could hint at new physics that diverges from the standard Big Bang picture. Scientists also conduct large-scale surveys of galaxies, examining their distribution to better understand how cosmic structure evolved under the influence of gravity and dark matter. Above all, curiosity remains our greatest engine. The more we learn, the more questions arise. And that might be the most profound realization of all. The cosmos is so vast, so ancient, and so speckled with mystery that our pursuit of its secrets is, in many ways, just beginning. Each discovery not only enriches our cosmic narrative, but also challenges us to rethink cherished assumptions. After all, if quantum fields and inflationary bubbles might spawn universes, then where do we fit in? Are our lives and consciousness just an accidental byproduct of complex chemistry and astrophysical processes, or is there something deeper to the tapestry of existence? Such questions border on the philosophical, and are sometimes tinged with existential wonder. Yet, there's undeniable beauty in recognizing that every atom in our bodies was forged in the nuclear furnace of ancient stars. Indeed, when we look at the cosmic timeline, we see a kind of interconnected continuity stretching from that tiny, hot beginning to the modern era, where we, as thinking entities, can reflect upon our origins. Humans have only been around a minuscule fraction of cosmic time, but across the epochs, matter assembled itself into galaxies, stars, planets, and, at least in our case, life that has become self-aware. This remarkable chain of events stemming from a nearly incomprehensible singularity offers a narrative that is both humbling and awe-inspiring, all of which returns us to the moment you look up on a clear night, gazing at the twinkling stars studding the sky. Each of those stars is a chapter in a cosmic manuscript that started countless eons ago in near impossible conditions of heat and density. Each one sits within a galaxy like our Milky Way composed of billions of other stars, and each galaxy is just a speck within a cosmos of untold billions more. And all of it, according to our best theories, emerged from a primordial seed that we call the Big Bang. Whether that seed was unique or part of a grander mechanism, whether it was the absolute origin of space and time or just a transformation from a prior state, remains a puzzle that pushes our imaginations to their limits. So, the next time you hear the phrase Big Bang, remember that it's less about something exploding into empty space and more about space and time unfolding in a magnificent, ongoing cosmic dance. It reveals a universe dynamic in its unfolding and epic in its scope, full of periods like the Dark Ages, episodes of intense starbirth, cycles of stellar death and rebirth, and a continuous interplay between known and unknown forces. From this perspective, our cosmic story is far from over. In fact, it's ongoing, with new discoveries waiting to be made by the next generation of telescopes, satellites, and curious minds. The Big Bang introduced us to a universe of staggering size, complexity, and wondrous stage on which we play a small, yet meaningful part. And that, in essence, captures the spirit of scientific exploration. Every answer we find leads us deeper into the mystery, illuminating the shadows of our ignorance while simultaneously revealing how much further we still have to go